Good morning, everyone. Here we are in Chapter 3, Lesson 1. Today we're going to explore the rest of differentiation, starting off with the chain rule. Now, the chain rule is a great rule so we can take the derivative of composition functions, such as f of g of x. We need the chain rule to find those derivatives when we have a function plugged into another function. Here, the definition of chain rule is that if you have some differentiable function and you allow u to be the inside function, g of x, and it's a differentiable function also, then the function f of g of x, which we call a differentiable function, can be differentiable in terms of x by thinking of dy dx as dy du times du dx, or the composition is f prime g of x times g prime of x. Notice that we take the derivative of the outside, hold the inside steady, and then take the derivative of the inside and multiply the two together. We're going to use Leibniz notation, which will help us with our u substitution. It looks a little more complicated than it really is. But basically, just like I said earlier, you multiply the derivative of the inside function by the derivative of the outside function. And we're good to go. So here's one example. If I wanted to take the derivative of this function without the chain rule, then I would have to distribute that binomial 5x plus 3 quantity squared, expand that to find that this is my polynomial. Then I could take the derivative as 25 times 2 and 1 times 30, and then the derivative of 9 is 0. But if we have the chain rule, using the chain rule, I'm going to take the outside function, which is this squared term up here. This is my outside function. Some function to the second power. That means my derivative of the outside function is 2 times whatever that function is, and that inside function is 5x plus 3. And then I want to multiply times the derivative of this inside piece, which is 5. So using our chain rule, the derivative should be exactly the same as this. We've got 10 times 5, and then 10 times 3, so 50x plus 30. Or if you wanted to leave it back here, perfectly okay to do that in AP Calc. If you wanted to regroup and keep it factored, that's perfectly fine as well. So either of these three would be perfectly acceptable. Here's a second one. Remember, it's the derivative of the outside times the derivative of the inside. So here you can see it's good to be able to decompose a function and recognize this 4 minus x squared is my inside function, and x to the third power is the outside function. So the derivative of the outside function is 3 times the inside function quantity squared, or 3u squared, and my u is 4 minus x squared, and then the derivative of this inside piece is going to be negative 2x. So just combining the two factors and leaving that inside binomial squared is a great place to stop. Let's see what comes next. So we have a general power rule that explains what we've just been exploring. Anytime I have a function of g, I'm multiplying the power times the inside function. I'm multiplying the power times the inside function and subtracting 1, and then multiplying times the derivative of the inside function. And here it's written with using e to a function. So I've got g prime in terms of x, and then the derivative of e in terms of x. So here, in this case, it might be easier if we rewrite f of x as x squared minus 1 to the 3/2 power. And then notice here's the inside, here's the outside, and find our derivative. F prime is 3/2, and hold the inside function steady. Take 1 off this power. Now multiply times the derivative of the inside, which is x squared minus 1. That derivative is 2x. And clean that up. In this case, the 2's could be removed. And we end up with 3x times the square root of x squared minus 1. Okay, and example B, since we've got this rational function, it may be simpler to rewrite this and move that binomial to the numerator and consider that a -2 power. Some people will find this easier than using the quotient rule. And -7 times -2 gives me a positive 14. Holding that inside function steady and taking 1 off the power gives us -3. And then multiply times the derivative of the inside function, which is 2. And it's just a matter of collecting like terms. If you don't want a negative exponent, we can move that binomial to the denominator and keep that a positive exponent, which is a trick we might have to use on some AP examples. In example 3, this one's pretty straightforward, so you might want to turn the video off and work through this yourself. Come back to see if your work looks like my work. Here I've got 2/3 to the binomial. Taking 1 off that power gives us a -3. The inside of the binomial, that derivative is -8x. And then cleaning up these common factors, looks like we have y prime with -16x in the numerator and 3 with a cube root of 5 minus 4x squared in our denominator. Okay, next on letter D, you have an e. So we know the derivative of e to the x is just itself e to the x. And when I've got something plugged in up here, I'm going to take the derivative of e to the x. This is a separate function, 3x squared. We're going to multiply by the derivative of 3x squared, which is 6x. So derivative of the outside, e to the u, and then the derivative of u, which gives us 6x e to the 3x squared for our final result. And then 2 more to go here, just for the practice. Again, I'm rewriting -2 times 6x plus 3 to the -1/3 power, taking the derivative of the outside. -2 times -1/3 is positive 2/3. Hold the inside function steady. Subtract 1 from the power, and then multiply by the derivative of the inside. That would be 6. Clean that up. 3 divides 6 2 times, and then our final result would be 4 in the numerator and 6x plus 3 to the positive 4/3 in our denominator. And then to finish this up with a trigonometric function, got to think about this one. This one is a little complicated. I've got cosine as a function. I've got a cubed as a function. And I've got an e as a function and a 5 theta as a function. So if you really break this apart, we're thinking of a cube on the outside, and then a cosine, and then an e, and then a 5 theta. So lots of stuff going on here. So let's be really careful. Looking at it this way, our derivative is going to be 3u squared. And all of this is my inside function we're holding steady. So we've got cosine e to the 5 theta. Okay, so 3u squared is like u cubed. The derivative of u cubed is 3u squared. Then next we're going to go look at the cosine part. So this portion, what's the derivative of cosine? That would be negative sine, and we're holding the e to the 5 theta steady. You see what I'm doing? Derivative of cosine is negative sine. Now what's the derivative of e? So the derivative of e is just e. And then finally, here we're holding the 5 theta steady. I'm going to rewrite that in red. So 5 theta. And then the derivative of 5 theta is just 5. You got that? So I had the cube on the outside, that's 3u squared. Then the cosine derivative, that's negative sine. Then the e derivative, that's just e. And then the 5 theta derivative, that's just 5. So our derivative, collecting like terms, is going to be negative 15 e to the 5 theta sine e to the 5 theta and cosine squared e to 5 theta power. Woo! That's first derivative. How did I get that second derivative? Go back and fix that. First derivative. Wow. Okay, let's see. Is this one a little more complicated? Letter G? No, this is pretty straightforward. So we could use properties of exponents on logs and pull that 2 in the front and have natural log of x squared plus x plus 1. So our derivative is going to be 2, and then derivative of natural log is 1 divided by x squared plus x plus 1, since the derivative of natural log is 1 over x, or 1 over u in this case. And if this is our u, then derivative of u is in the numerator, 2x plus 1. So that one's pretty straightforward. And then letter H, let's see, we could say, we need to clean this up a little bit. So you've got e to the negative 4 natural log of x could be thought of as e to the natural log x to the negative 4. Now this property lets me bring x to the negative 4, because e to a power, that's just canceling out that logarithm rule. E to the ln of a is just a. So we're thinking about this function, f of x, as x squared times x to the negative 4. Well, if we use properties of exponent laws, that's just x to the negative 2. Because when you multiply 2 powers with the common base, you add the powers. And then that derivative is negative 2x to the negative 3rd power. So thinking that through, I'm just going to put that 3rd power on the bottom. So this entire lesson is just mostly just practice until we get to example 4. So we have a few more here. Here, g of x, do you see the 2, the squared is the outside term in both cases, and this is a difference, so we've got to be careful to do both pieces of our derivative. So we've got 2 cosine 4x. Derivative of cosine is negative sine. Don't lose the 4x. Now take derivative of 4x. And then subtract the derivative for this. So 2 sine, hold on to the 4x, times derivative of sine, that's cosine, 4x, and then take the derivative of 4x, that's 4. Let me move this over a little bit, give myself some room here. Okay, so we're going to clean that up. And what does that look like? We've got a negative 8 cosine 4x times sine 4x in our first piece. And over here we've got a negative 8 cosine 4x sine 4x. They have terms in common. Wait, I missed this. Negative. This is negative 8 cosine sine. This is negative 8 cosine sine. We could add those together. Negative 16 cosine 4x times sine 4x. Okay, they're getting tougher. Here we got another product with a product rule with a chain rule. So product rule says if you have a function times a function, we're thinking of derivative of the first, hold the second constant, plus hold the first constant, take the derivative of the second. This piece here is going to be a chain rule because the second function, our g function, is a composite function. Okay, so take a deep breath and let's give that a try. We've got the derivative of the first is 4x cubed, and don't touch the second function. Okay, so this is the f prime times g. Plus, we want f times g prime. So this g prime has the chain rule in it. And holding f constant, that's x to the 4th. And we're going to multiply that times the chain rule for sine squared. So 2 sine x to the 1st power. And then derivative of sine is cosine. Now take a look at that. Can we clean that up in any way? Maybe collect like terms. Regroup things a little bit. How about 4x cubed sine squared x, and then we could put 2x to the 4th sine x cosine x. Now, you may want to stop there, or if your teacher wants you to factor some more, we could factor out a 2x cubed sine x and leave inside 2 sine x plus an extra x here, x cosine x. It just depends on which you want to do. Now on a free response test, if you didn't need to look for a completed or a collected set of terms, it would be okay to stop back here unless you needed a number or some specific form. Okay, I think 4 more examples. Let's see. This one, a natural log embedded in a natural log. So we've got h prime, the derivative of the outside piece, is 1 over the inside function. Don't touch that. Then the derivative of the inside piece is 1 over x. So our final derivative, collecting like terms, is 1 divided by x times natural log x. Letter L, we've got a sine function with an e and then a pi x plugged into all of that. Outside derivative is cosine. Hold e to the pi x steady. The derivative of e to the pi x is just e to the pi x. We're multiplying that times the outside. And then our last one, the derivative of pi x is just pi. So it's chain, 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 see? And f prime of x is going to be pi e to the pi x power times cosine of e to the pi x power. Ooh, these are hurting my brain. And then here we've got another cosine. So if you think about it, if this helps you to write it out this way and keep your thought processes steady, that may help you. It's not a bad tool to use. Your derivative of g prime of theta is 8 cosine pi theta times, cosine's our second function, that's going to be negative sine pi theta, and then pi theta is our third function. The derivative of pi theta is pi. So g prime of theta would be negative 8 pi cosine pi theta times sine pi theta. Or if you want to interchange those around, you can do that. Multiplication is commutative. And then here, one last time, let's rewrite this to look like tangent of 2x minus 3 to the 1/2 power. So our derivative for tangent is secant squared, and we don't want to change that inside function, 2x minus 3 to the 1/2 power. Then this derivative for the square root is 1/2 to the 2x minus 3, subtract 1 from the half, and multiply times the derivative of 2x minus 3, which is 2. Then collect like terms. The 2's can be removed, and our final derivative would have secant squared for 2x minus 3 under the radical. And then this piece is radical 2x minus 3 in the denominator. Danger beware. Don't cancel. Don't cancel. I know you're tempted. Don't do it. You can't cancel. Okay. This one, we're going to look at derivatives using the table, so let's see what this is about. If we let the function f be continuous and differentiable from 0 to 1, and we know that g of x is the f of 4x, the table below gives the derivatives values, which is the derivative of f of x, and we want to find the value for g prime of 2. So here's our g of x, it's defined here. And if the g of x is defined as the f of 4x, then first, before we touch the table at all, we want to think about the rules for the chain rule. So the chain rule says to take the derivative of the outside function, don't touch the inside function, and then multiply times the derivative of the inside function, which is 4. And then we're wanting to find the g prime of 2/10. So we can do that very simply by just replacing the x with 2/10 and reading what this is letting us know. We want to do the f prime of 4 times 2/10 times 4. And that looks like we've got the f prime of 8/10, because 4 times 2/10 is 8/10 times 4. Now I can go look at the table. At 8/10, our derivative of f is 1.125. So 1.125 is that derivative times 4, and that gives our g prime of 2/10 is 4.5. You want to check me on your calculator, please do. So using a table, a real AP style question there. We got one more to go. Use the table below to complete the following. We want to find the equation of the tangent line at -1 if h of x is defined to be this composition. So just like the previous example, we want to find the derivative in general form, which is 3f prime hold g steady times g prime. And then we want to substitute -1 because we're going to find the equation of the tangent line. So we need a slope for the tangent line at -1 on our composition function. So it looks like I need to figure out what's the g of -1. So the g of -1 is -1. So right in here we've got a -1. Does that look familiar? The f prime of -1. And then what's the g prime of -1? Well, the g prime of -1 is 2. So we could replace this expression with a 2. And then the f prime of -1, we need a new number there. So the f prime of -1 looks like it's 4. So 3 times 4 times 2, which gives us a slope of 24. So the slope at -1 is 24. And to write the equation for any line, we need a point and a slope. That means I need to look at -1. What's our x and our y on -1? So we have a -2, but our function is 3 times that, right? The f of g of -1. So we've got to figure that out. Let's get a new sheet of paper here and look at dual page. So I have a place to write. Got a slope. This is our slope. And then we need the point when x is -1. The h of -1 is 3f times f of g of x, and our x is -1. So the g of -1 is -1. Oh, my tablet's messing up here. Doesn't like me doing this dual screen. The g of -1 is -1. The f of -1 is -2. So we have 3 times -2. Yeah. Let me stop this dual screen thing. It's not behaving well. That looks like a mess. Whoop. So when x is -1 in our composition function, our y value is -6 because we had 3f of g of x. And our x was -1. The g of -1 is also -1. The f of -1 was -2. So we have our point. This is our point. And we had our slope. And our slope was 24. And they want us to write the equation of the tangent line. So the tangent line, using point-slope form, is going to be y equals the slope times x minus the x value, that was -1, plus the y value, that was -6. So our slope was 24, and our ordered pair was -1, -6. You needed a point and a slope to write the equation for the tangent line. Okay, one last example and we're done. If j of x is the composition times cosine, so it's a product rule, what's the value of j prime of x? So last thing, j prime is a chain rule. So remember, we're going to think of this as do the chain rule here. And if we called that k times h, then we would do derivative, hold that second, and then hold this one steady, take the derivative of cosine. You ready? So j prime is going to be f prime g times g prime times cosine plus, hold the composition steady, f of g of x times derivative of cosine, which is negative sine. Okay, so the j prime of 0, we're going to have to go back and look at our table again, is going to be f prime g of 0 times g prime of 0 times cosine of 0 plus the f of g of 0 times the sine of 0. So this whole half can get eliminated because the sine of 0 is 0. And this piece cosine, this is 1. So we just really need the g of 0, the f prime of g of 0, and the g prime of 0 off of our table. So let's go back and look. We're going to do this piece first, the f prime of the g of 0. So the f prime of the g of 0. So the g of 0 is 2. The f prime of 2 is -2. So let's go back and put that in there. So the g prime of 0 is the f prime of 2, and that was -2. And then we need the g prime of 0. And the g prime of 0 looks like -3. So times the g prime of 0, that was -3, times 1, -2 times -3 times 1 tells us that the g prime of 0 is 6. So this is the chain rule. Take your time and think about things carefully, and you'll master this in no time. See you in lesson 2.